Okay, this will be the last part of the lecture. We're going to talk about the types of catalysts. So there are four types: photocatalysts, homogeneous catalysts, heterogeneous catalysts, and enzymes. Okay, so first up, photocatalyst, what is it? It is actually one of the products of the reaction itself, and it carries out its catalytic activity as soon as it's formed. All right, so one example that we have here is your manganate reacting with ethane dioic. So when the NM2 plus is formed, it actually catalyzes the reaction. So when you look at the graph of rate versus time, right, you realize that the reaction starts very slowly, and then once the NM2 plus is formed, it increases exponentially. All right, and then after that, it starts to go into a decrease and tapers off because the concentration of reactant becomes lower. All right, so if you plot a concentration of MnO4 minus against time, you can see that the rate actually is very slow at the start. It becomes very, very fast, and then it tapers off again when the reactants are depleted. So that is your autocatalyst. All right, so let's look at homogeneous catalyst. What does it mean when we say there's a homogeneous catalyst? It means that the catalyst is in the same physical state. All right, so they actually react with the reactants and then to form the intermediates, which is then consumed to form the products. All right, it is regenerated at the end of the reaction. So anything that is classified as a catalyst must be regenerated at the end of the equation. All right, so we have this example of the reaction S2O82 minus with I minus. Okay, so you can read the description of this particular reaction. What does the homogeneous catalyst of iron do? Okay, it actually reacts with each of the reactants, all right, and then itself becoming different what do you call it, different oxidation state. All right, so you can see that the iron 2 plus, right, got oxidized to iron 3 plus, and then subsequently it will react with the iodide, and again it forms back the iron 2 plus. So what it does is that it becomes an intermediate between the two reactants. All right, and because it is positively charged, there's no repulsion between this catalyst, the iron, and the two reactants. Okay, conversely, you can also start with iron 3 plus, which will then react with your iodide, all right, to get reduced to iron 2 plus, and then it goes to react with your S2O8 and regenerates Fe3 plus. All right, so your energy profile diagram, it looks like this. Okay, with no catalyst, but with catalyst, you can see that the EA lowers drastically. It lowers drastically. Okay, another example is the oxidation of sulfur dioxide is catalyzed by nitrogen oxide. Okay, so this I think you will learn about this in your organic chem. All right. Okay, the last part is heterogeneous catalyst, which means that the catalyst is in different physical state. All right. So what do? They provide alternative reaction pathways, same as the homogeneous, but the method by which they do so, right, is they increase the local concentration of the reactant particle by letting them, stick on their surface. All right, and they also help to weaken the chemical bonds in them for the reaction to happen. Okay, so the Born-Haber process is one which you are familiar with. Okay, so for heterogeneous catalysis, right, it involves transition metal. Okay, because transition metal have partially filled d orbital and they give a active surface, right, so that they can bond with them. All right. This, like what I said earlier, it weakens the bond and bring them closer together, lowering activation energy. All right, so you can read this example. Okay, the last type of catalyst is your enzymes. All right, the bio people will rejoice here because this is like very, very easy for them. Okay, what are enzymes? They are globular proteins that increase biological reactions. All right, they are very sensitive to temperature and pH and highly specific. They only act on certain substrates. All right, substrate is your reactants lah. It's a bio way of saying it. All right, so the substrate must have the right shape to fit into the active site. The active site is like the place where the reactants react. Okay, so the biologists call this the active site. So the enzyme is said to be saturated when all the active sites are occupied, okay, by substrates. All right, so we're going to look at the graph of rate against the substrate concentration. So you can see that the Vmax, right, the maximum rate that you can achieve by increasing concentration of the substrate. All right, so all the enzyme active sites are occupied, then you will achieve the maximum rate. Okay, so at low substrate concentration around here, the order of reaction is 1. The rate of reaction is directly proportional to the substrate. Okay, at high substrate concentration, the order of reaction is 0 because it's no longer dependent on the substrate concentration. Okay, somewhere in the middle, we have a mixed order. All right, because the active site are not fully saturated, but neither does the rate of reaction react proportionally, okay, to the increase in substrate concentration. Okay, so let's do a quick check from a November question. So we have this uncatalyzed reaction. When we add in NO, right, the catalyst, it participates in the reaction. So it is a homogeneous catalyst. It has the same physical state. Which reaction pathway is the most appropriate? Okay, so the uncatalyzed reaction is shown as a dashed line. Okay, so the answer is A. All right, because you can see that your how do you work this out, right? You can cancel these two, which are the intermediates. All right, so basically you have to form an intermediate. So this means that C and D, which does not have intermediates, will be out lah. All right, so comparing between A and B, right? What is the difference between them? Okay, you can see that the EA of the first step is very much lower, whereas for B, right, they are around the same. Okay, so which option A or B is most appropriate? Oh, sorry, I beg your pardon. I realized this has nothing to do with the EA. It's more to do with the difference of the final energy of the products. Okay, it should be the same. All right, not different. Okay, that's why B is out. All right, so the last part of the notes, we're going to look at Arrhenius equation. So the effect of temperature on the rate constant, right, is as T increases, right, rate constant and rate also increases. Okay, for catalyst, EA decrease, the rate constant and hence the rate increases. All right, so those are actually quite common sense and logical. Okay, so with this, we come to the end of kinetic lecture.